Hello students, today the topic that we are going to learn is rotational motion. Rotational motion is a large topic, so we will cover the basics of it so that in later classes we can go further and continue from whatever we have left. We will be leaving it today. So in today's class we are planning to cover three things. First, center of mass. Then center of mass in case of two particles. Case of a system of particles where there are many particles, or say infinite number of particles. And third being continuous body. And other than this, we'll learn about some basic concepts related to rotational motion. So what kind of concepts we are going to learn? What are the basic physical quantity that is related to rotational motion topic, and how we use them in solving numericals or understanding other types of topics. So let us go ahead and start with center of mass. So what basically is a center of mass? Suppose there's a point mass situated at a point A having a mass small m. You might have heard about such assumption, like assuming there's a point mass somewhere, assuming that one point mass collides with another point mass, or one body attracts another body while both are situated at a single small points. But such things seldom happens. We often get bodies with large volumes which are not confined to a single point. The question is, why do we assume that body is confined to a single point? That's because it makes calculations easier. So in basic part of mechanics, in kinematics, we have used this thing, that a body is a point mass, or a body is located at a point. What happens when there are two bodies? Again, we are assuming a body with a point mass. One have mass m1 and another have mass m2. If I'm assuming that they are inseparable, there is no continuity in this mass, but they are not separable. And if I'm pulling this thing or pulling that thing, how will this thing behave? Like, would I consider that the mass is here at A or at B? This thing is answered by the concept of center of mass. Center of mass tells us that when we exert a force, or whenever some other quantity, this set of mass, this system of mass is affected by any external factor, how this system of mass will act. So center of mass tells that which point we can assume as the mass wherever the mass is concentrated. And for that, Let us consider this situation. Suppose point A is located at a distance x1 and point B is located at a distance x2. Then the center of mass will be somewhere between A and B. Let us say this is the point. So how do we get to know what is this point? And for that we need one thing. First relate this one, m1 with x1. Later you will come to know that this is the moment because of this mass. So m1 x1 moment by this mass located at B is m2 x2, and the distance x1 plus x2. Sorry, I just wrote the wrong thing. m1 by m2, the masses m1 and m2, and this is the distance of our reference point. So if A is distant from point O by x1 and B is distant from point O by x2, where m1 is located at point A and m2 is located at point B, then some point, let's call it C, will be given as m1 plus m1 multiplied by x1 add m2 multiplied by x2, the whole divided by m1 plus m2. Let us try and work out an example problem for this. Let's say from a point O, 5 meter distant is located a point mass 2 kg and another 10 meters, that means from O another point is located which is 5 kg in mass. Then what is the center of mass of these two particle mass system, say two particle system? We can simply apply this formula and our point C would be m1 x1, and here m1 is 2 kg, x1 5 meters plus m2 x2, m2 is 5 kg and x2, you can see x2 is 5 meters plus 10 meters, 15 meters, 5 multiplied by 15 divided by the sum of two masses, m1 plus m2, 2 plus 5, and this will be, the unit here is meter, we are getting 5 times 2 times 5, 10 plus 75, 5 times 7, 15 divided by 7. It is coming out to be 85 by 7 meter, or about 12.1 meter. I hope this part is clear. So we'll move and find out what is the case when we have many point masses. Like this was a simple problem because we have only two masses, and for which we could calculate our center of mass using just this small formula. So what happens if there are other parameters like more than 2 point masses, and this is the only dimension is not x1, there are other dimension x2 also, sorry, other dimension being y. वैसी कंडीशन में हम क्या करेंगे? तो पहले हम let's look at this in two particle system only. So what happens? One particle A, one particle B. You may see that I have taken it on XY plane. XY plane पे किसी भी पॉइंट के दो कोऑर्डिनेट्स बन के आएंगे. We can say A है x1 y1 और B है x2 y2. अगेन A पे हम मान सकते हैं मास m1 और B पे मास m2. So what will be the center of mass? Obviously it will lie along this line, along the line AB. Let me try and write this more clearly. It will be something like AB, and C will lie somewhere in between depending on कि m1 और m2 के बीच का रेशियो क्या है. तो जैसा हमने सिर्फ x कोऑर्डिनेट्स के साथ किया था, like you can see m1 x1 plus m2 x2 divided by m1 plus m2. वही चीज हम x और y दोनों के साथ करेंगे. m1, सो कह सकते हैं हमारा सेंटर ऑफ मास का x कोऑर्डिनेट होगा m1 x1 प्लस m2 x2 डिवाइडेड बाय m1 प्लस m2, और y कोऑर्डिनेट होगा m1 y1 plus m2 y2 divided by m1 plus m2. इन दोनों इक्वेशंस को देख के आप ये अंदाजा लगा सकते हैं कि अगर मास m1 मास m2 से बड़ा है तो सेंटर ऑफ मास m1 के ज़्यादा करीब होगा, और अगर m2 ज़्यादा बड़ा है then center of mass would be closer to the other mass m2. Similarly, जब हमारे पास कई पार्टिकल्स होंगे और हमारा जो टोटल मास है कैन बी टेकन एज अ सेट ऑफ सेवरल पार्टिकल्स, हम इसी फॉर्मूले को बड़ा करके मीन्स something like m1 x1 plus m2 x2 plus m3 x3 and so on divided by the total mass m1 plus m2, or say the total mass m. कह सकते हैं इसको थोड़े क्लियर तरीके से लिखते हैं. Whenever we have a system of particles of say n number of particles, x of center of mass or x coordinate of the center of mass is m1 x1 plus m2 x2 plus so on mn x1n. divided by x1 plus x2 and so on xn. Mathematically, in summation form, we can write this as summation of I to n mi to xi divided by, again I have made a mistake, sorry about that. Please look, I have written x1, x2, xn. It should be m1, m2 and so on to mn. So the total mass being summation of mi, that means m1 plus m2 plus m3 to mn, or say if we are assuming summation of mi or m1 plus m2 and so on to mn is equal to, let's say, capital M, then this expression here is summation I to n mi xi divided by capital M. Similarly, the y coordinate of the center of mass comes out to be summation of I to n mi yi divided by, again, the total mass m. So however large this number in the number of particle, we can go on and work it out. So say we can work out 1 particle system, 2 particle system, 3, 4, or say even 1000. But say it is in lakhs or crores. Can we do it? नहीं कर पाएंगे, क्योंकि हमारा कोई भी कैलकुलेशन सिस्टम हर पार्टिकल के मास और उसके पोजीशन को कैलकुलेट करने के बाद कहीं ना कहीं थक जाएगा, उससे आगे का कैलकुलेशन नहीं हो पाएगा. For this we have one way which we call integration. You might have already been familiarized with this. So you also might have also studied that summation when continued in a very small scale is termed as integration. So if we are considering a continuous body, can we say it has thousands or millions of points in it, which we can say that each point has very small mass and very small volume, that small that it can be said to be confined to one small point having no volume at all. But can we go on and apply that formula? xcm and ycm is something like summation of xi mi divided by m and yi mi divided by m? No. Why? Because we don't know the location of each point. We don't have the capacity to carry out that much calculation. For that, what we can do, we can divide this whole this continuous mass into small masses. Say assume that this has very small thickness and the mass is also very small, suppose dm, and it is located at a distance x and it has thickness is also very small. So we can say that the x coordinate, the total x coordinate of the center of mass of this whole continuous body will term to be x dm what are we doing? We are integrating this whole thing, divided by dm. When we have all other sets, suppose another dm, so sum of all small such small parts, we are integrating that. So our x of cm, center, means x coordinate of the center of mass, is integral of x dm divided by dm, or x cm is equal to x dm 1m. Why 1m? This thing comes out as m, as the total mass, because what we are doing, we are summing up all the mass present in the body. Let us try and work it out in a real scenario where we can utilize this integral method and find out what is the center of mass of that continuous point. Let's consider a thin rod. A very thin rod, we can consider this as an object in only one direction, because it has no depth or no height. It only is present in its length. We can consider that we can relate this with the first example that we worked, finding the center of mass of two particle system in x direction only. So here what we are doing a continuous system instead of a 2-point system, and finding the center of mass, which might lie somewhere here. So, and our reference would be one of the endpoint. Consider this one endpoint as A and this endpoint as B. So, and the center of mass would be obviously the x coordinate, because this whole object has no other dimension. It doesn't have y coordinate, and it doesn't have a z coordinate. So we can say xcm is equal to 1 by m, and what is m? Mass of this rod, this very thin rod, into integral of x dm. What is x and what is dm? So x, let us say we assumed a mass dm here, which is present at a distance x from point A. So our center of mass would be at a distance this. Considering the length of this rod be L, then x dm, dm is, this is a continuous rod, so what do we call it? Whenever we are considering a thickness or a length dx, the mass content would be proportional to the whole mass. So dm would be equal to m times dx, this small thickness length dx, divided by x, because we can say the density of mass along its length is, or say the lengthwise density of mass is m by x. So the total mass concentrated in the length dx, dx being dm equals to m into dx by x. moving ahead, we are putting this value here to dm. Center of mass is 1 by m into integral of x into dm, m into dx by x. This whole part is complete here. Let's go ahead and cross out x, numerator x and denominator x. We get xcm am I missing something here? Okay, I'm missing one thing. Okay, I'm missing one x that should be present here outside of the yes. We know that we have just made a mistake here writing this x here. That is wrong. This should be, let me mark it with a different color. The density of this whole linear density of this whole rod would be m divided by L. So that would be this comes out to be x dx divided by 1 by L. Sorry about this confusion. Let me rework this so that there's no confusion left. So xcm is equal to 1 by m integral of x times, here dm equals to m by L into dx, into m by L into dx, which comes out to be 1 by m into, taking out m and L out because they are constants, m divided by L into integral of x dx equals, m gets crossed out, 1 by L, and we know we are integrating this from point A to point B. So what is distance from point A to point A? 0. And what is distance from point A to point B? L. So integration from 0 to L, we are getting integral of x is x square by 2. So x square by 2, getting the limit 0 to L, and that we get 1 by L into L square by 2 minus 0 square by 2, that's 0, and that gives our center of mass xcm equals L by 2. Also, by symmetry you can see, since the mass is equitably distributed throughout this rod, we can say that the geometrical center of this mass, this whole body, would be present at would be the center of mass of this rod, and the geometrical center is at L/2 from either end. So, and this is what we derived using this formula, this whole calculation. So what we covered so far, we got to know about a 2-point system in a rotational motion. We got to know about a system where there could be multiple points, where there could be multiple point masses, and then we got to know how to find the center of mass of a continuous body. Just like a rod, we can work out other continuous bodies like a square, like a rectangle, like a circular sheet. Now let's talk about some basic concepts related with the rotational motion. So when we say we apply a force on an object of mass m, we know that it is accelerated, and acceleration is equal to F by m. And this is what we study in linear mechanics. What do we know about rotational mechanics? Why rotational mechanics is even needed? तो rotational mechanics में हम ये कह सकते हैं कि हमें हमेशा point masses नहीं मिलते. We always have to deal with a continuous mass in which we know that there are forces acting, लेकिन उनका exact position उनके center of mass से होगा या नहीं होगा ये तय नहीं है. Suppose कि किसी बॉडी पे फोर्स इस तरह से लग रहा है कि द पॉइंट वेयर फोर्स इज एक्टिंग, जिस पॉइंट पे वो फोर्स लग रहा है वो उसके सेंटर ऑफ मास से L डिस्टेंस पे है, और उस लाइन पे, यानी जिस लाइन से होके वो सेंटर ऑफ मास से जुड़ा हुआ है, उससे वो फोर्स एंगल थीटा बना रहा है. ऐसे कंडीशन में हम ये मान सकते हैं कि सिंस दिस इज द सेंटर ऑफ मास, दिस शुड मूव लाइक दैट, बट दिस force being not along the center of mass, this will cause a tendency to rotate, and this tendency is known as torque. So you can say torque is equivalent to force in rotational mechanics. It is not the same quantity, but it does similar kind of thing. In force tend to accelerate a body linearly, while torque tends to accelerate a body angularly. Means ये किसी बॉडी को टर्न करा सकता है, रोटेट करा सकता है. So that's how torque is. And how do we calculate torque? Torque is written is this symbol. We call it tau. Tau is equal to F into L, or say to be more standardized, we call it R. F dot, or say F cross R. If you have studied about vectors, this is torque is equal to the vector product of F vector and R vector. If you have not studied about the vector calculation or vector addition or vector multiplication, don't worry, there's another formula. This is the simplified version. The modulus of the torque, or say the magnitude of torque, is equal to force, that is the magnitude of force, times the magnitude of this distance r times sine theta. The ones who have studied vector multiplication would simply see that the vector multiplication of two vectors a and b would result into ab sine theta, while theta being the angle between a and b. Simply f और r के बीच में ये theta angle है, so that's why this whole calculation is going like fr sine theta. So one of the basic concepts related with rotational mechanics is torque. Let us move ahead and learn another. Earlier we have studied momentum. What is momentum? Momentum is mass times velocity. Similarly, in rotational mechanics, we have angular momentum. Just like in the laws of motion, laws of linear motion, we know that force is the rate of change of momentum. Torque is the rate of change of angular momentum. We will learn about angular momentum more. Torque is equal to rate of change of angular momentum. And how does this further gets formed into an equation? Just like F equals to ma, tau is equal to mass. The equivalent of mass in rotational mechanics is I, that is moment of inertia, into alpha. And what is alpha? Alpha is angular acceleration. So let us see, let us say this is a wheel, and it is moving, it is rotating, being at the same point. Suppose the axle is present here and it is fixed, and it is rotating clockwise, and say it rotates angle theta in 1 second. So we can say that it has some kind of velocity, but how? Angle velocity is not considered with respect to angle. Velocity is considered with respect to distance. Distance divided by time, or say displacement divided by time, is velocity, and distance divided by time is speed. So what is angle divided by time? So angular displacement, this theta can be said to be angular displacement. Angular displacement theta by time is known to be omega, or angular velocity. And can we say that this omega, or angular velocity, will be uniform throughout the motion or rotational motion of a body? No, we can't say that, because it may change over time. Their torque might be acting on it, and that may change the angular velocity over time. So the rate of angular velocity, or say d omega by dt, is known as alpha, which we call angular acceleration. So let's summarize and see what we have learned so far. We learned the concept of center of mass, we learned the concept of center of mass in terms of 2-point system, multiple point system, and a continuous body. We saw how the concept of center of mass and the formula of x1 m1 divided by m was translated to form the center of mass of a rod which is located at a distance L by 2. And then we came to know about some basic concepts of rotational mechanics, first being torque, angular momentum, which is I omega, I being the moment of inertia, omega angular velocity, angular displacement, that is theta, angular angular velocity, we just said omega, and angular acceleration. Angular acceleration, we give a notation alpha, and we also came to know that tau is equal to tau as torque is equal to I alpha moment of inertia into angular acceleration. Again, angular momentum is equal to I omega angular moment of inertia times angular velocity. So we will keep learning and continue from here. Till then, happy preparations and do good in your exams. Thank you. Bye.